Multivariable control poses a unique set of problems. For the first time, we will have to make decisions about what controlled variables should be coupled with what manipulated variables. So when we look at our diagram for a 2x2 multivariable system, we see that we have two inputs connected to the two outputs going through these transfer functions over here. And what makes this a multivariable system is the fact that this first input affects both of the outputs through one of these routes. The same goes for the second input through one of these routes. Now, this poses the question, which one should I use in order to control which output? So the first version of this is called a 1-1 or diagonal control pairing, where we simply use the first output to control the first controlled variable. And we will have two controllers, one which is connected to the first controlled variable and one which is connected to the second. So controller 1 manipulates manipulated variable 1, which controls controlled variable 1. Controller 2 goes through manipulated variable 1 to control controlled variable 2. Now, in order for this to work, we obviously need to measure these variables. So we will measure y1 and subtract that from a set point for y1 going into controller 1, and we'll add a measurement of y2, subtract from YSP to going into controller 2. So here we have the full control configuration. Now we mean for this configuration to use the first variable to control the first variable and the second variable here to control the second variable over here. But as you can see, there are some additional loops that are formed while we are trying to do this. So we can see that the primary loops, I'm going to indicate these primary loops over here. So this is the first primary loop, and this is the second primary loop. So we call these primary loops because this is what we intend to happen. And then there are unintentional coupling loops, which go along here. And so you can see that there's a loop that forms all the way around, going through this controller, going through this controller, all the way around here, going through this controller as well. And so a change in any one of these variables actually has a full effect, and there are these two or this additional coupled loop that is drawn in orange. So make sure that you understand that a change here will have an effect all the way along this loop. So we'll measure that effect, the second controller will act on it, that action will be moved back, and we'll see that effect in y1. And so this control loop actually contains the other controller as well. So this controller, which we designed using this transfer function over here, will also see an effect from this secondary loop. Now we could have made a different decision. We could have used the manipulated variable 2 to control controlled variable 1. And what that would look like is our first controller would actually be connected to U2, while our second controller would be connected to GC1. all of the other calculations remain the same. So we'll still have a set point, except that this set point will be the set point for still y1, but we are manipulating u2 to do that, and we'll have the same calculations over here. Now we have what is called an off-diagonal pairing, or a 1-2-2-1 pairing. So these calculations get quite complicated quite quickly if you try to work out the closed loop transfer functions that correspond with these diagrams. My recommendation is that you very quickly learn to recognize the sub-blocks that form when you look at these diagrams. And so you can clearly see that the block here is actually representing the system, and that this block over here is representing the controller. And now it's just a case of finding out how to represent those in the mathematical notation. So it's quite simple to start with the system, and when you see a full configuration like that, we've already seen what that looks like. So we just have a matrix containing each of those elements in the natural order. So this GP 2, 1, GP 2, 2, and so that's the system. I'm starting here with the off-diagonal controller because it helps us to think a little bit about how this is working. So what we have here is, again, we'll have a matrix. So we'll have GC is equal to a full matrix, and we now have to reason about how the blocks are arranged. So we can see that this first error goes through GC1 and then goes to U2. And remember that we can associate the columns of the transfer function matrices with the inputs and the rows with the outputs. And so we can ask ourselves, the first input of this matrix is connected to the second output. And so therefore GC1 must be in this off-diagonal position over here. So that's the first input and the second output. The same goes here for GC2. And there are no connections between the first input and the first output, or the first or second output and the second input. And so we end up with this block diagonal form. Now, why this is important is because it makes the calculations very much simplified from here, because now we simply draw exactly the same block diagram. We've got y as p, but except we now understand that y as p is a vector of values. We have gc, except we understand that that is now a matrix of values. And we have gp, again understood to be a matrix. And we can now work with the closed loop transfer function in matrix form. And that makes our calculations significantly easier. Now, how that works is through the block diagram algebra. So I'm going to include some additional symbols here so that we have something to refer to. And it's important to kind of go through this one slowly first, since it is going to become quite difficult to manage with the matrix algebra. So we have to go slowly at first so that you understand that these symbols are not commutative. And so we can see that we have three equations, one corresponding to each block. So we've got y is equal to GPU, and we've got u is equal to GCE, and we've got one corresponding to the sum, which says that E is equal to YSP minus Y. Now these three equations we need to manipulate in order to obtain the closed loop transfer function. Unfortunately, SymPy cannot handle non-commutative block diagram algebra, so you will have to learn how to do these simple ones by hand. Now, luckily, it's not that difficult. We can substitute u into that equation over there to eliminate u, and we can then substitute this equation into there to eliminate e. And we're then left with an equation which only features u and y. So let's just write that out. So we've got y is equal to gp gc ysp minus y. So now that we have this equation, and notice that I've taken great care to substitute these equations in place, taking care that the multiplication happens on the same side. This is an important point because with matrix algebra, multiplication is not commutative. So the final step is to get rid of the second y in this equation. So we can see that we've got a y over there, but we've also got a y over there. We simply multiply out and collect terms. So we'll end up with y is equal to gp gc ysp minus gp gc y. And when we rewrite that to be on the right hand side, now also keep in mind we're going to be very careful with sides. So we have y plus gp gc y is equal to gp gc ysp. And now we have to collect these left-hand terms. The way that we'll do this is we'll take out an I and GP, GC. This is a very important step which often confuses people. Make sure that you understand how the I comes from extracting the Y over here, and make sure that you always keep the vector on the right of the matrix. Well, if you keep that rule in mind, you'll never make a mistake with sides. So now we have GPGC YSP, and the last step is to multiply by the inverse of that left-hand matrix. So we have Y, and notice we are multiplying from the left, Y minus GP GC inverse GP GC YSP, and now we have a transfer function for this closed loop block diagram. Now, please note that this is the same transfer function that we would have obtained with the diagonal controller pairing. Even though this slide started with the off-diagonal controller pairing, we are getting exactly the same equation, which will save us effort. I recommend that you go once through the textbook in the worked out examples where they do this using the scalar equations, and just familiarize yourself with how difficult that is. Compare that to the method that I've shown you now using matrices, and I'm sure that you'll agree that it's significantly easier. Once we have this in this form, SymPy can do all the calculations for us using SymPy.matrix notation.